What's up, folks? This is Pierre-André Mathieu, and I'm here today with a tutorial on how I organize my Calculate Character Collision function within the character blueprint. Now, the reason why I'm doing this is because I have a comment and suggesting that I say what I see rather than explaining how it works with appropriate order, and I'm doing the best I can to explain in how I made a few corrections, hence using an effective method, more precisely the macro method. So, that being said, let's get started. So, going to the character blueprint, as you can see here, I have repel actors and repel vectors. And what I have here is clear nodes. They likely represent clear or reset operation. When I clear the node with repel actors, whereas I calculate the repel. Okay. Before I calculate the repulsion with actors, players, and enemies, I have to clear any previously stored data about the specific actor involved within the repulsion. The same, however, can be said with repel vectors. How is it used? Well, if I find reference, you can tell that it's being used basically with every other macros that I've created. As with the repel vectors, alright. So yeah, simply put, what I'm doing with these is clearing or resetting repel actors or vectors before initializing any actor or vector. That being said, I think it's high time I move on. What I have here is facing through. This macro makes a decision based on the boolean name face through. If it's true, then the execution will continue along with face through. But if it's false, the execution will continue along the false output, thereby using this, in which I'll get to after this. And as I double click, it stems from this. The purpose is that it encapsulates a specific piece of logic relating to checking if something is facing through. Now, I'm gonna click references here. In initiate animation or start animation or begin animation, whatever you would like to call on your function, it uses face through. So in creating this macro, I created this logic for it to be reusable and easier to understand within the blueprint. So the core logic here is that this macro receives the face through boolean that determines which output will be executed. If it's true, the macro will flow and continue along with facing through. But if it's not, the execution will continue without facing through. And that's basically the idea here. The next macro that I've created is repel spheres loop. And the purpose of this node is to iterate through the collection of repel spheres, in which I have right here inside. It triggers the start of the loop when a signal is received from the repel spheres array, which is the sphere collision that I use for the character right here. That way we can repel other existing enemy types. What we have here is for each loop, and the array we're using here is repel spheres. How it's triggered is that the input receives the signal, which means that we're starting the loop. When the loop begins processing in the first repel sphere to the collection, it is outputted through the array element Pin. The loop body output is triggered, which means it's sending a signal next. Okay, I'm pretty much stuttering here. Okay. When the loop body output is triggered, it sends a signal to the next node within the sequence. The loop moves to the next repel sphere and repeats 3 to 4 steps. It continues until every single repel sphere has been processed. It can be used to calculate repulsion forces between repel spheres and other objects, such as boxes, crates, tables, you name it. Additionally, it can be used to update the positions or philosophies of ray spheres only based on their interactions. In terms of visual effects, it can be used to animate or control a group of spheres procedurally. Most likely during fighting against multiple enemies, if possible. The key points that I would like to bring up is that the custom loop that I've created here is likely made to encapsulate a specific piece of logic. The array element suggests that the loop is iterating through the collection of repel sphere objects. The input and the loop body manipulates the flow of execution within this visual programming. Now that I have that, the loop body, it uses for loop, not for each loop. For loop, which is the one I have here. The first index is 0. The last index is 1, which means that it can be used twice. The loop body uses player enemies loop, and the input index stems from select, which is customizable like it is now. But the thing is, I'm using players and enemies, both of which are character blueprint variables from player game mode. Now what I have here is players and enemies loop. This customized node iterates through players array or enemies array based on the input index. It's most likely where the index from the for loop is linked to, depending on which array, either players or enemies to process. The loop body triggers the code block linked to for each element that is selected. The data output right here offers current element, either player or enemy, being processed within the loop. This sort of thing can be used for a lot of gameplay mechanics, like turn-based actions, where you perform actions for all players, then all enemies in turn-based system, or alternating behaviors, which applies a different logic or effect to players and enemies in an alternating fashion. Let's go inside here. Okay. What we have for input is that it defines parameters for this customized node. The execution input triggers the node's logic. It's likely an integer input that dictates which array to process. 0 for players or 1 for enemies. With our getGameModeBlueprint function, we cast the game node to specific player mode type, which allows us to gain access to its properties and functions. This select array, the one we have here, allows us to choose between two arrays based on the input pin value. Option 0, we have players. For option 1, we have enemies. And because we're connected to the custom node's input pin, we dictate which option to select. When we return our value, we provide the selected array for each loop, which iterates through the selected array, whether it's the player or the enemy. With our array element, we provide the current element for player and enemy to be processed. Now, we're not going to... No, I'm sorry. Scratch that. Array index and completed it is not important because there's no reason why it should be used. We don't have a specific integer that would allow us to do any sort of calculation, so array index is out of the question, and we don't have anything for us to complete, so this one is also out of the question. Then from loop body and array element, we have repel spheres without facing through. As the title suggests, we're encapsulating the logic for iterating through repel spheres and performing some action, more precisely when we're not facing through objects. Now, as you can see right here, the self represents the object or actor facing through check applies to. And what this indicates is it's using the character blueprint object reference. This right here is the execution output. It triggers the code connected it for each repel sphere that meets the not facing through condition. And the array element, which is the sphere collision object reference, provides that we are currently repelling the sphere which is being processed, similar to what we have to our spheres loop node. So this node is basically a specialized version of repel spheres loop. It adds condition only to process repel spheres when the character blueprint object reference is not facing through something. The self here receives. The self here is basically a receiver, especially when it comes to things like this. So what we're doing here is that we're receiving players' enemies loop with the use of the character blueprint object reference. In case if you're confused, this is the character blueprint that we are referencing. Going inside here, we're checking if we are using phase through a custom node to check if the object reference we're using, which is the character blueprint, is currently facing through anything. The node iterates through the repel spheres, executing the loop body for each sphere and providing that the sphere through the array element output. The loop is skipped or doesn't execute the loop body. It's possible when we use this method to apply repulsion forces between the character and the repel spheres only when that specific character is not facing through anything. This prevents unintended interactions while facing. On top of that, it can be used to start visual effects or other actions related to repel spheres. That's only if self-object is in a specific state. So, the key factors to consider is that this macro builds upon the previous version of repel spheres loop, as it adds a facing through condition. It has more complex logic, which makes the blueprint more modular and readable. The exact implementation of facing through, check, and loop logic would be defined within this macro itself. So yeah, after we have that, we have this: calculate world location and distance. Oh, and fair warning, this may be a bit complicated, so you're going to have to bear with me on this. Okay, what I have here within the input are two things in which need more addressing. I'll call it sphere collision reference. I'll call this one scene reference. And for that, I'll call it the sphere array element. Yeah. Before I get onto this, I want to explain again what this blueprint entails. Excuse me for repeating myself, but I want to explain things in proper order, in a way that you might get. And I'm doing the best I can to my ability. Alright, so let's explain how this works. This input within repel spheres loop without facing through defines the input parameters on this macro that I've built. I'm gonna have to call this character reference, for lack of a better word. Yeah. The character reference is used for our character to check if he's facing through or not. The execution here is the triggering node in terms of overall logic. Inside here, the node determines if the character is facing through anything. So, connected to the self, so the target input connected to the self. Oh no, hold on. I'm gonna stop here. I think I'm thinking too much. Alright. So, the character reference is connected to the self input of this customized macro. using the branch we have here, it will execute only if the character is not facing through. Actually, it's the other way around. The true output will execute only if the character is facing through. However, if it's false, the character is not facing through. But what we have here is an inverse version, which means that we're not determining if the player is facing through, we're determining if the player is not facing through anything. If it's true, then the character doesn't face through at all. But if it's false, then the player is facing through something. And since we are not facing through anything, we're going to have a continuous loop with the repel spheres, which can only be used through the character reference. Once we have those, we're going to be using calculate world, location, and distances, which uses the logic from both repel sphere swoop without facing through and repel sphere loop. Most notably, the array element from the sphere collision object reference. The purpose of this node here is it calculates and outputs world locations and distances related to both object and actors. It utilizes the inputs of sphere collision reference, scene reference, and sphere array element. And out here, it uses first world location, second world location, added float, and distance float. The first world location provides the world location and of the scene reference. The second world location and likely provides the world location it basically provides the world location from of the sphere array element. When we add the float, we calculate the value based upon the input value and objects involved. The distance float output provides distance between both sphere collision in reference and sphere array element. So this one here takes multiple references as an input and performs calculations regarding to their world positions. It holds a lot of data points, including world locations and a potentially calculated distance. There are possible scenarios when using this. In terms of AI and physics, this macro can be used to determine the distance between objects for AI pathfinding, collision detected, or applying forces only based on proximity. Additionally, it can be used to calculate the distance between a player and enemies, or between different environmental objects like boxes, crates, tables, cars, desk, you name it. It can also be used to specifically place objects in a world based on calculated distance or relative positions. In animations, it can be used to drive animations based on the distance between objects, such as a character reacting to an approaching object, like a wrecking ball or a moving car. Anyway, the key takeaway is that this macro encapsulates the logic in calculating world locations and distances between objects and characters alike. Its exact calculations performed and purpose of the input pin and added float outputs would be determined within this very node itself. It also promotes codes reusably, and it also promotes code reusability and organization by abstracting away details, location, and distance calculations. And as I go inside, this is where I organize all of that. As you can see here, I have two at world locations. This one retrieves its scene reference, whereas the second one retrieves sphere array element. The distance vector node calculates the vector between two world locations. The vector length node. I don't know if I have a vector length. I don't know if I have a vector length node, but I do have these. And what I'm doing with the float addition is I add the sphere radius is of sphere collision reference and to the sphere array element. With the branch node, I can compare the distance float to the result of float additions. If it's less than the combined scales of radii plus of the input value, then and only then can I contain the repel actors. Well, to be more precise, can determine whether or not I can contain repel actors. But more on that after I explain what this doohickey does. But if the distance is somehow greater than or equal to the combined values, like the ones we have here, it basically does nothing. The first world location is connected to the sphere reference, whereas the second world location is located to the sphere array element. The added float it connects to the result of these two float. The added float links to these float functions. with the distance float connected to this vector with the distance float connected to this minus float we can determine the distance between these two objects. So what I'm getting at here is I get locations to retrieve locations, and from sphere collision and sphere array element. Then calculate the distance between these two objects. And after I calculate the distance between two objects, I get the scale sphere radii of sphere collision reference, scene reference, and sphere array element. Then add scale sphere radii and input value. Also, in comparing the distance, I have to check if the distance is less than the combined values. And once I have that, I can provide world locations distance and the result of these float additions. So this node checks if two objects are close enough to each other considering the scaled sphere radius along with the additional input value. The added float output may represent a threshold distance or modified distance value used for further calculations. The branch node's output could be used to trigger different actions based on the proximity of such objects. The best possible scenario would be when the collision detects with the buffer or proximity-based actions. The node can be used to detect collisions between objects within the buffer zone, only dictated by a scaled sphere radius and the input value. It could also trigger actions or events based on how close the objects are to each other, like applying forces, playing sounds, or triggering animations. So the key takeaway that I'm getting at is that this node encapsulates a much complex logic in relation to the object proximity and distance calculations. Its exact purpose of the input pin and added flow outputs may require further context or analysis of how this node is used in a much larger blueprint. Also, it demonstrates the power of custom nodes to create reusable, organized logic for game development or visual programming applications. Okay, now that I explained the complicated stuff with the world location and distances, I can explain to you how this works. Can contain repel actors likely checks if a certain object or action can hold repel actors. This blue circle here represents the object or actor in which you want to check for the ability to contain repel actors. And what this does is it finds an item in reference to character blueprint. This macro takes an object reference as an input and determines whether that object has the capacity to contain or hold repel actors. It could be based on various factors like object type, properties, or tags. As for the possible flow of execution, the node receives a reference to the item to find object. It performs a check to see if the item to find object meets the criteria for containing repel actors. Considering the check either to be true or false, output is triggered. The best possible scenario would be the best possible scenario in terms of game development would be inventory or interactions. The node could be used to determine if a player character or an inventory object can hold or store repel actors. It can be used to control interactions, like allowing a player to pick up a repel actor only if they have the appropriate container. For level design, it can be used to define specific places or objects within a level that can hold repel actors, potentially influencing gameplay or puzzle mechanics. For AI behavior, this macro can be used to manipulate AI behavior, like having an AI character seek out and collect repel actors only if they have the capacity to carry them. Now this is just one of many possible scenarios. Not guaranteed. I want to make that clear. let's get inside and see what we have here.
Sometimes when you're here, I can't feel no doubt, 'cause you keep me where the stars are bound. It doesn't really matter, 'cause you're here.
This input here is the object reference you want to check for containment capability. And this is likely a customized function or macro that I created to perform the actual containment check. It takes the item defined as an input, likely has internal logic to dictate if the object meets the criteria for containing repel actors. It outputs a Boolean variable indicate whether the object can contain repel actors. So I have output connected to the output of contains node. The node will execute true only if the object is contained. It can execute false only when the object cannot be contained in any shape or form. Simply put, we use this node to receive the object reference to check, then use contains node to determine if we can contain repel actors. Based on the results of that check, we execute either the true or false output. So, key points. The macro provides a reusable structure for checking object containment, in which contains node encapsulates the core logic of containment check. With this modular approach, I can make my blueprint more organized and easier to comprehend.
Sometimes when you're here, I can't feel no doubt, 'cause you keep me.
Now that I have that, what I have here are, okay, if this is true, then I can repel actors and vectors only if the array element is set. However, if it's false, then all I can do is normalize repel actors and vectors. Okay. I know what you're wondering. Just how does repel vectors influence the repel actors? Okay. I'll put you in a way you might get. When the player gets close to the enemy, he moves the enemy without facing through. The player character is approaching the enemy character, which means that the system detects that the player is getting close to the enemy, likely using the Calculate World Location and Distances node to determine their proximity. The system needs to prevent the player from facing through the enemy while still allowing interaction or collision. This is where repel actors and vectors logic comes to play, because the system likely uses repel actors and vectors blueprint to calculate a repulsion force or movement vector, as is likely based on the distance between the player and the enemy, their scale, sphere, radius to prevent overlapping, and potentially other factors like the player's velocity or movement direction. The calculated repulsion vector is applied to the enemy character, causing it to move away from the player. With this movement, it prevents the player from facing through the enemy by creating a dynamic buffer zone between them. The system likely has a collision detection mechanism which keeps both the player and enemy in place, making sure that both cannot physically overlap or intersect. It might involve using collision spheres, physics simulations, or other techniques to enforce solid boundaries between characters. But most notably, I prefer to use this method. So this behavior suggests that the system is made to create a dynamic and responsive interactions between both players and enemies, rather than blocking the player's movement when they get too close to the enemy. The system actively pushes the enemy away, creating a more natural, believable interaction. With this approach, avoiding the issue of the player getting stuck or glitching into the enemy if they were to apply directly is plausible, because in moving the enemy, the system maintains a separation between these characters while still allowing for close quarters combat or other interactions. So the key takeaway is that the entire system uses repel actors and vectors logic in terms of calculating and applying repulsion forces to enemies, as the repulsion prevents the player from facing through the enemies while maintaining dynamic interactions. This system likely incorporates collision detection mechanisms to enforce solid boundaries between characters. Of course, there are things to consider. The strength and direction of the repulsion forces is may be adjustable to fine-tune the interaction as the system could incorporate additional factors like the player's attack actions or the enemy's AI behavior to create more multifaceted and interesting interactions. With this approach, it can be extended to other objects or characters within the game world to build a more immersive, dynamic environment. So, the overall purpose of Calculate Character Repulsion is meant to be a core component of a system made to manage dynamic interactions and collisions between both players and enemies, and repel actors within the game's world. Its main functions include preventing facing through, dynamic collision response, conditional interactions, modular reusable logic, This node calculates distance between objects and determines buffer zones based on scaled sphere radius. The use of repel actors and vectors calculates and applies repulsion forces to keep both players and enemies from facing through, thereby creating dynamic collisions. The function serves to utilize a lot of conditions and checks to manipulate the flow of execution and dictate when to apply repulsion. The players and enemies loop iterates through player and enemy objects, allowing for specific interactions and behaviors depending on their roles. Now, I could go on and on and on, but I rather not hurt your brains a lot because, well, as the person says, too much information, in which apparently I'm displaying here. Anyway, I'm gonna go straight to its benefits and considerations. So, with the Calculate Character Repulsion system, it provides a more immersive, believable interactions based on dynamic collision responses, prevents player and enemies from facing through other collision-related glitches, offers modular reusable code for easier maintenance and future development. It has potential for crafting more complex and nuanced interactions and based on a lot of conditions and factors. As for consideration, it's possible that fine-tuning the strength and direction of repulsive forces in order to achieve the desired behaviors. We could add more factors like player actions or enemy AI to build more varied interactions. Also with it's possible to extend the system to get better handling of interactions with other objects within the game's world beyond just the characters. So yeah, that's basically the gist of what I'm getting at here with the Calculate Character Repulsion. Now, let's see the results of what I'm getting at here. As you can see, it works. Now, I've done all I can to explain to you how the Calculate Character Collision system works within a character blueprint, explaining how it works with appropriate order. Forgive me if I gave in way too much information, but for now, this is the best that I can do, but somehow I will improve upon it. If you enjoy this, if you enjoy what I'm showing you, don't forget to like and subscribe to my channel for future videos like this, and keep in mind that what you take and learn from me is yours to do with as you see fit. Peace out and enjoy the rest of your day.